So we're going to continue with this introduction to the Girdle-Firstein completeness theorem. And again, I'll be following the text that's here. Essentially, I'm talking at the moment from page 92. So let's recap a little bit of what we did last time. Okay. So we talked about coding of, first of all, formulae. We decided that for each formula phi, we could associate a number called its Girdle number, GN, or just code number. And we could just check, there's a computer program to check, given a number, whether it's a code number of a properly formed formula or not. And likewise for terms in our language. There's a computer program that would check whether something codes a term or not. So with that idea, we then thought about proofs. So proof is a finite list of formulae, or if you like, a finite string of Girdle numbers. And we looked at how we could code a whole string here of Girdle numbers, just the simple idea of using primes. So if I've got m numbers to code up, I can use the first m primes here and use these values here to give us exponents for the primes. So each proof, or purported proof, or string of strings, string of string numbers, gets itself a code number here. And the idea is that being a code of a proof is also something that we can check using a computer program. So we call it effectively decidable. So in particular, what we've got is putting a more mathematical hat on it, is we've got characteristic functions of whether something is a formula. This is f of form of x. This is a 1 or a 0 if x codes a formula. And this is f of proof. Perhaps I should say proof in the system Q. If x is a code of a decent proof. And what I emphasized was that we could check whether a proof or number codes a proof of some particular formula sigma. What you can't do is have a program that will just say yes or no as to whether there is a proof for that formula sigma. It's an existential statement. We then generalized that. We thought about extending this idea. Q only had 7 axioms. But the idea was we would also think about systems that extended Q. And as long as we had an algorithmic method for testing whether something was an axiom, so we've got, when we look at the characteristic function of code numbers for axioms, returning 1 or 0 if x is a Girdle number of an axiom in T or not. As long as this function is also computable, we just use the same idea again. Right? We can look at proofs from T down here. So then there's a characteristic function of something being a proof in T. Right? And if x is a code for this, the function returns a 1. Otherwise, it's a 0. And again, the emphasis that I was saying before, this is not saying that we've got a computable, or as I was also, I'm going to call them recursive functions, right, that will return a 1 or a 0. Because checking a proof is fine, but actually is computable. But actually providing a proof is not necessarily. Right? So we're not saying that there's a recursive function g that will, when I put in a code number for a formula that I'm interested in, will return a 1 or a 0 if there's a proof or not. Okay, any questions there before we move on? Okay. So let me share the screen for a moment here. Okay. So we also looked at, and I said you don't have to memorize these ideas here. I actually gave what a mathematical definition of what it means for something to be the kind of counterpart being effectively decidable is this collection of recursive functions. And so recursive functions were built up using a successor function, a zero function, and a projection function, and using some idea of recursion here. This is not too, how these things are built up are not too important for us. But the idea is that this is a mathematical idea. And it turns out that any of the recursive functions that we can think of, we can program. And nobody's been able to think of a definition of computability whereby it computes a function that's not recursive. So these seem to be the same kind of thing. And on the top of page 92, you can see, well, repeating a little bit of what I'd already said on paper this morning and yesterday, right? That we've got these functions here, which are effectively decidable. But what I'm claiming is that we can just find recursive functions that'll do the same, that are the same thing here. And we define in a set of numbers x here to be recursive, or in the literature it's called decidable, if there's a recursive function f, which is the characteristic function of x. It returns us a 1 or a 0. So proposition 6.8 is just the counterpart to 6.4, right? It just says that all of the things that we've been talking about, I can think of as being given as recursive sets of numbers in the sense of this definition 6.7. So the following sets of code numbers are recursive. The only difference is before I was saying algorithmically decidable or effectively decidable. Here we're just saying they're characteristic functions given by recursive functions. So the notion of being a formula term or an axiom or being a code of a proof using our prime power idea. So all of these sets of numbers, they've got recursive characteristic functions. And the expansion of the idea is to say, again, if I take axioms extending Q, as long as I've got a recursive function that's the characteristic function of code numbers of axioms in T, this is I'm calling F sub T here, right? Then being a code of a proof using prime powers, using predicate calculus and the axioms T, then code numbers of proofs also are recursive sets. So the footnote here at the bottom is saying, well, actually, nobody's managed to think of a definition of a computable function that doesn't produce precisely the recursive functions. And so this isn't, so the assertion that every computable function is a recursive function, right, is essentially it's the Church-Turing thesis here. So stated in slightly different words, right, the Church-Turing thesis is that every effectively decidable property or algorithmic property is in fact computable on a Turing machine. Right? Or in other words, a computer. Right? But everything that's computable on a Turing machine is actually given by a recursive function. So this isn't a mathematical statement. You can't prove the Church-Turing thesis because it talks about all kinds of effectively decidable or algorithmic properties that we might think of in our heads without actually saying what those are. And I mean, as we think on the next, going through the next 3 lectures, it doesn't matter too much what you have in your head as to whether you have the idea of a recursive function as basic, or if you have the idea of something just being computable as basic. Because if we accept this Church's thesis, anything that's computable is recursive. And anything that's recursive is also computable. Okay. Just one more thing before I turn the share off. Along with this idea here about recursive functions, suppose I've got a k-place recursive function f. Well, there's actually a formula that will give me, as it were, the graph of this function here. If f of this k-tuple is this value m, right, there's a formula corresponding to f, which will be true of these numbers here, if f of n vector is m. So again, I just want to make this kind of plausible, right? We're not going to go into this. Right? What is a recursive function? Well, it was something built up from those basis functions using composition and recursion and so on. It's a little finite tree of how we build up recursive functions from basis functions. So every recursive function's got a kind of construction. It's a little tree of how we put the function together. Well, then the formula just reflects that idea. Right? The formula also just specifies, as it were, says out loud, how that tree is put together that gives us the function. So I hope it's just kind of plausible that there is such a formula that corresponds to this recursive function here. It wouldn't be terribly illuminating, but a bit messy to actually kind of literally write out the formula each time for a recursive function. But for example, for the basis functions, those with a successor 0 functions and projection functions, it's easy to write down a formula that corresponds to those, the 0 function or the successor function. And likewise, when we build something up in a more complicated fashion from the basis functions, there's a way of doing it. So you just write down that way of doing it to give you this formula phi. So in short, the recursive functions are just kind of definable in the standard model of arithmetic. There's a formula that we can write down that describes them. Okay. So we're talking about, for example, this function f sub proof here. Perhaps let me switch to paper at this point. what we have here is, let's see, adjust this. So we've got this function here, which is talking about proofs in Q. And it will say that n is a code number of a proof in Q of this formula sigma, and this will be 1 here. If and only if this says there exists n so it is the prime power code number of a proof from or in Q, let's say in the system Q, of the formula with code number sigma. Or code number that of sigma. Yeah. So I'm going to define here, what is this, these corners, and around here. And this is going to think of this as this number here is, and this will be the, as it were, the numeral, the term that names the Girdle number of sigma. So here, so this is the term. With en of sigma many primes up here. So this is dashes, let's call them dashes, not confuse them with other primes. So this here, right, so this is interpreted as the Girdle number of sigma, right, in the natural number structure. Right. So I think of this as a numeral here for this number. For the number 2. So this is the real number I'm talking about here. And this thing up here is the numeral for Gn of sigma. So again, to go back to the line above, I got a, sorry, f of this proof in Q here. So to say that this here is 1, right, here, right, is to say that, okay, this characteristic function, this is n, this is a prime power code of a proof, genuine proof, and on the last line is, once coded, is the formula sigma here. So we have that this idea here, this can be given to us by a recursive function. So this part here, right, this is a recursive, right, or computable function. So by proposition, if you believe proposition 6.9, so there's some formula, let me just call it 5pf down here. Let me just check what I've got in my notes here. So what we have is that n here is a model of phi of f of pf of n sorry, I want to back up a bit. I can see I've got two things happening in front of me. So there's a formula phi sub pf here. Okay, right. So there's a phi corresponding to this f here. So this is the f function here, n and sigma and 1. So this is going to give me the graph of this function here. Right? So n will think this number n is a code of a proof whose last line here is the formula sigma. So this happens if and only if the above. Equals 1. Here. And okay, so this will happen, right, over here. So if Q proves sigma, then there's going to be some number that's a code for that proof. It's a proof of Q in sigma. And this will happen if and only if there is an n such that this is 1. Okay, so then this will give us this left-hand thing here. So in short, so I'm making a bit of a dinner of this. If Q can prove sigma, there's some formula that's true in the natural numbers that says, okay, there is this n is a code of this, is a code of proof. It's a code of a proof of sigma. Yeah. Okay. The next bit that we need to look at is the diagonalization of a formula. So let's consider this formula here. So here's the numeral for 10. Let's say 2 brackets here. Here's the numeral for 2. So this is a formula in our language here. So I'm writing 2 here. This is just an abbreviation for something with 2 primes in it. Up here, 2 dashes. And 10 would have 10 of these things. So in the notes, these are boldface, but I can't write boldface just using this pen. So what actually, if we interpret this, what is this saying? This is saying that x as a decimal number ends in a 2. It's some multiple of 10 plus 2. So if I look at this formula, I interpret it in a natural number structure. This says, okay, whatever x is valued as, or interpreted as, has as a decimal number, its last digit is a 2. If x happened to be a Girdle number of a formula, then having last digit a 2, if you look back at the coding, means the formula ends in a right-hand bracket. It says the formula ends in a bracket. Because we agreed to code up brackets here by the number 2. So this way we can, since we've coded up formulae as numbers, we can express using simple number theoretic expressions here certain facts about those numbers which code those formulae. So this is saying, okay, if this is a Girdle number of a formula, the formula ends in a bracket. So in this way, we can kind of use codes to refer to formulae. What we want is a code that in some sense can refer to itself. Sorry, a formula that can refer to itself. And we get this through this trick of girdles, of diagonalization. So if I've got a formula in the language, so it's called the diagonalization of Psi, is another formula. So it just says there exists x such that x is the code number of Psi, but also and Psi holds. So it looks a little strange at first. So I would urge you to look at exercise 6.3. Which perhaps helps to understand this a little bit. If you look now at example 6.12, so let me share the screen here. There's various examples then of formulae and their diagonalizations. what have we got here? We've got the very simple formula y equals 0. Right? So the Girdle number, if you look at the code for this formula, it's 676. So what would the diagonalization be? Well, there is x, as x equals this numeral for this code number, so 676 here, and then conjunction with the formula. Well, the formula is y equals 0. So here's a formula of the language L. It says there is a number, so that x equals 0 with 676 dashes after it, and y equals 0. Now in the far column, I've just put down, is this formula true or false in the natural numbers? So we'll just look and inspect it to see. Well, this whole formula is only going to be true if y gets assigned 0. Right? I mean, there certainly is something that's 676. And this will only, the truth or falsity of this diagonalization just depends on whether we interpret y as 0 or not. So when y is 0, it comes out true. Okay, let's look at the formula x equals 0 here. Okay, its code is 576. Here's the diagonalization. There is x as x equals the numeral for the code number, and then the formula. So here's the numeral for the code number 576, and we put its conjunction with x equals 0. Right. Okay, this diagonalization is always false because x can't be 0 and 576 at the same time. Here's the code number for x naught to 0. So again, the same idea. There is x as x equals this numeral, and there's the formula again, x is not 0. Okay, and this is true, right? Because in the natural numbers, 0 is different from 145762, right? So those are simple examples. Here's a more sophisticated example down here. Now we take the formula phi over here to be this example that I gave above. So recall this was the formula that said if x was a Girdle number of a formula, that formula ended in a right-hand bracket because the number ended in a 2. So here's my formula phi. Let's abbreviate. Let's just say its Girdle number, whatever it is n sub 0. Right, is the Girdle number of this guy here. So the diagonalization, according to this definition here, is there is x. So x is the numeral for n0, and then the formula itself. So I've written out phi here. So this diagonalization, this formula, right, this is true, right? Because the Girdle number of this phi ends in a 2. And why is that? That's because phi ends in a right-hand bracket, which you can just see above my mouse cursor here. So this is the formula that comes out. This is a formula whose diagonalization is true. Just happens to be so from the way that we've written it out like that, from the way we've chosen it. Yeah. Okay, are there any questions? Okay, the next lemma says there's the characteristic function of this diagonalization idea is recursive, right? So I won't go through this because I said I'm not going to go through building up recursive functions. So you can read this as just saying computable. Right? So the idea is that we've got some formula psi associated to this diag function. And the idea is that diagonalization of n, right, if n is the Girdle number of a formula, is the Girdle number of the diagonalization of phi. Okay, so up here, suppose n is the Girdle number of psi, then diag of n is the Girdle number of this formula here. So what is the diag function? So if n is the Girdle number of some formula phi here, then diag of n, this is supposed to be the Girdle number of the diagonalization of phi. And to be then explicit, what is this Girdle diagonalization? It's this one. So the diag function takes the Girdle number of a formula and returns to you the Girdle number of the diagonalization of the formula. That's why we call it diag. And again, just look, it's just a completely algorithmic process. You give me this number, right? And I can decode the number and check it's a Girdle number of a formula. So I've got n, I've got the formula. So now I write down this formula here using this numeral for n in here. I've got this formula here, and now I just compute its code. And that's the answer. That's what the Girdle number of the diagonalization is, and that's what diag n is. So given n, it's a computable process to find diag n. To go from n here to diag of n. Right, if n is the Girdle number of a formula. So I say it's a computable process, and what 613 does is just say, okay, I can find a recursive function that is diag. Well, it says diag is a recursive function. But as I said, you can think of this as just saying it's a computable function. Here. So we'll skip over the proof of the justification of this. What the proof of 613 does is, if you think about it in computing terms, computable terms, it just tells you how to do the computation. So it just tells you how to do that computation. And if you glance through it, you can see how that how that happens. There's an explicit description of what diag is. So 614. So phi is a formula of the language. And now let's suppose the free variable of phi is x. So psi is the diagonalization of phi. So what does this mean? Again, I'll just to remind us, this is saying there is an x. This is x equals the code numeral for phi and phi. So this is literally what psi is, right? Then the lemma says, it's just spelling it out. So this is a sentence, this psi, because the only free variable of phi is x. So there are no free variables in this thing. What the right hand is saying is that phi is true of its own code number. And the lemma is just saying that's equivalent to psi being true. But indeed, that's all. It looks kind of mysterious, but actually this is all it's saying, right? What is psi? It just says there is something which is the code number of phi and phi of x wholes. Right? Phi has only got this free variable x in. So there is an x. X is the code number of the string phi and phi of x wholes. Okay, well, here's the x being put into phi. Right? So this is going to be true in n exactly when psi is true here. So this is just what the diagonalization says. And that's just psi. Again, that's in this case, right? Because phi just had this one free variable. So we now get a theorem about the undefinability of truth, right? So Tarsky's theorem. So this says there's no shortcut to finding the code numbers of undefinability of true sentences. You might think that there's a way we could define in n the set of all the code numbers of true sentences in n. This theorem says no, you can't do that. There's no formula psi so that for any sentence, sigma if sigma is true in n, if and only if this formula here is true of its code number. So there's no formula I can find that will define the set of code numbers of truths in arithmetic. So we suppose for contradiction there is a formula. So there is such a formula psi, and I'm going to assume that psi's got a free variable y. It's got to have some free variable in, so I can put in some numbers right here. So I choose the formula with a different variable from x. That's the point. So now we say let phi of x be, there is a y, here's the formula that defines the diag function, and now we say not psi of y. So again, here, this says there is a y such that y is diag of x, right? And not psi y. So here, this holds if and only if y equals diag of x. And now we build on this again, right? We let chi be the diagonalization of phi x. Right, so again, what is chi going to be here? It's going to say there is an x, and this is phi. Again, phi is free variable x. This is what chi is. So by the previous lemma, I've got that n chi comes out true in n if and only if phi holds of its own Girdle number here. So if I write out the latter here, so this here, the right hand here, this happens if and only if so I'm just writing in now out what phi is. The psi diag of diagonalization of phi here and not psi y. So what does it say? There is something, it's the diagonalization of the formula with its code and not psi y. But chi is the diagonalization of phi. Right? So this y that's being referred to here actually is the code number of x. Oh, sorry, code number of chi. So chi is the diagonalization of phi. Okay. So this happens if and only if n here is here and again not psi. So chi is the diagonalization of phi here, and not psi holds of it. So putting this together, we have, okay, n chi is true in n here. If and only if, well, there is this, which we said was the same as this happening of chi. Right? So chi actually is the diagonalization of phi. So this is a true relation about numbers. So this holds then is meaning that this holds here. So we have this holds if and only if not psi chi holds, because this always holds here. So we're going to have this if and only if this always holds, so this if and only if this, which is what I've written here. But what is our supposition on our formula? The formula psi is supposed to be such that it's only true of numbers if they're code numbers of formulae that are true in n. Right? So if psi is false of something that's a code number of a formula, this means the formula can't be true in n. And that's the situation that we've got down here. Psi is supposed to be false of this chi here. So then we have that this here is equivalent to saying that n here is, this chi does not come out true in n. So I've now got a contradiction here. So there's no such. There's no such. So this is a contradiction. There's no such. So there's no such psi. And that finishes the Tarsky theorem. Sorry, that was a little bit quick towards the end. But the idea is that there's no shortcut to finding the truths of arithmetic. There's no formula that will define for us the set of code numbers of truths. So that's the moral there.